Okay, so guys, last time when we were together, if you remember, we talked about how to solve that problem where you figure out the molecular mass of the solute, and it ended up being a big day. So when we walked out, we talked about this idea of trying to stay on schedule, and in order to do that, because we want to get the test in before Christmas, we talked about the idea of you guys going home and watching that short screencast over intermolecular forces and some of the applications of that. I'm not going to ask you to publicly confess whether you did that or not. But guys, what I would like to do is come to this idea of vapor pressure, because this tends to be something that's a little confusing for people. So let's do this. Rather than publicly have you talk about whether or not you understood this or not, I'm just going to spend a little bit of time and review vapor pressure with you. If this is not a review because you didn't get to this, that's fine. But I do think that this is going to be worth doing, spending a couple minutes and talking about vapor pressure. So guys, I would encourage you to include this in your notes, whether you were a part of well, if you already got this in your notes because you watched the video, that's up to you. But you know me, the only way to learn something is by drawing a beaker. So guys, if you don't have a beaker that represents vapor pressure, I would encourage you to at least do this in your notes, and then you're going to find that this quickly leads into what we're going to do today anyway, and so it's not a waste of time. So when we talk about vapor pressure, guys, draw yourself a beaker and draw yourself a liquid. Actually, better yet, I'm going to draw my beaker to the left. So draw yourself a beaker, draw yourself a liquid. So guys, imagine that this liquid is something like water, and as we call this water, we're just going to let these circles represent our bent water molecules. So guys, let's talk. What holds the water molecules together? Which intermolecular forces? Hydrogen forces. Does it have dipole-dipole forces? Yes. Does it have induced dipole forces? Yes. But the strongest force in the neighborhood is hydrogen forces. And so we will just say that hydrogen forces holds this together. But guys, understand that even though this thing is held together with very strong hydrogen forces, some of these molecules on average have enough energy to jump into the air, basically. I mean, they're jumping out of the beaker. And when they do, what do we call that process? We call it evaporation. So guys, we've got molecules on average that have enough energy to overcome the intermolecular forces that are holding them together, and those things evaporate. And when they evaporate, where do they go? Away, right? They go away. Well, guys, let's keep go away from happening. So put a lid on your beaker. So now that you have a lid on the beaker, where do the molecules now go? Well, not away. And so what they end up doing is they end up getting collected up here in the space above the liquid. So guys, now we have a vapor that is trapped above the liquid. And those molecules are running around at hundreds of miles an hour. They're running into each other. They're running into the walls. They're running into the surface of the liquid. They're going crazy, bouncing all over the place. But guys, the idea is that because these molecules are running all over the place and pushing out, they create a pressure. And we call that pressure vapor pressure. So guys, the vapor pressure then is the pressure of the vapor, and the word we use is supported. So it's the pressure of the vapor that is supported by a liquid in a closed container. So guys, let's pause for a minute. Does that, whether you watch the screencast or not, questions about what vapor pressure is? Does that make sense? You guys okay? Okay. So then guys, do this. Draw yourself another beaker. And now in this beaker, let's put CH3OH. And again, we'll let some circles represent our molecules. And now, guys, these dudes jump up into the vapor phase. And we'll put a couple more over here, maybe. So, guys, methanol, which is CH3OH, which is an alcohol, that also evaporates. That creates a vapor. But, guys, the question then becomes this. How are the vapor pressures different? Which one will have a higher vapor pressure? The methanol on the right or the water on the left? Which one's vapor pressure? And don't read anything into the number of circles. Because which one would have a higher vapor pressure? Left or right? Go ahead. The one on the right. Why? Exactly. So, guys, that's the thing that makes this weird. It's an inverse relationship with intermolecular forces. So the idea is that the intermolecular forces, guys, we're actually reviewing the last thing that you should have picked up from the screencast. We haven't got into new material. We are talking about vapor pressure. So just join the conversation because this is the important idea. So, and you said that very well, Preston. The idea here is that methanol has weaker intermolecular forces. Because the intermolecular forces in methanol are weaker, it's easier for those molecules to jump into the vapor phase. And as a result, the vapor pressure in the methanol would be higher than the vapor pressure in the water. Does that make sense? Okay, so then, guys, it brings up some interesting questions. So here's what you know. There's an inverse relationship between intermolecular force strength and vapor pressure. So what about this? What about volatility? Which one is more volatile, the one on the right or the one on the left? What does volatile mean? Evaporates readily, right? So, guys, which one is more volatile, right or left? The right. So, guys, there's a relationship then between vapor pressure and volatility. So the more volatile a liquid is, the higher its vapor pressure will be. Doesn't that make sense? If volatility is its ability to evaporate, the more readily this evaporates, the more readily it goes into the vapor phase. And so those are directly related. Does that make sense? Okay, so what about this? Guys, what could we do, back to vapor pressure, what could we do to change the vapor pressures of these? So let's just focus on one of them. Let's focus on water. What could we do to make the vapor pressure go up? Heat it up. So, guys, vapor pressure is directly related to temperature. You heat this up, the molecules move faster, they have more energy to break the intermolecular forces. Now, guys, what could we do to drop the vapor pressure besides cooling it? Obviously, cooling it will drop it. What else could we do to drop the vapor pressure? Add salt. Because, guys, if we add a solute to this, for the same reason that adding salt makes the boiling point go up, adding salt makes the vapor pressure go down, because now we've got ions in the solution that not only attract the molecules, strengthening the intermolecular forces, but remember, we also talked about the idea that if this guy wants to evaporate and he runs into an ion, he's just going to bounce off. So the idea is that not only does this increase the boiling point, it also decreases the vapor pressure. So, guys, I would suggest that wasn't a waste of time. Questions on vapor pressure? You guys okay? Yeah? To what? We are not. No, and I know that that's on your mind because of that video that you saw. We don't even know what critical pressure is yet, but understand as far as this class is concerned, critical point, critical temperature, critical pressure is just going to be this far off like science fiction thing that we're going to know exists. We're not going to do a deep dive on it like you've been simply because we don't need to. But we will look at it in a minute and we'll talk about what it is, but we're not going to do a deep dive on it because we don't need to. So, guys, questions on vapor pressure and things like that? You guys okay? All right, so now that everybody's back, welcome. And guys, we're going to move on from here. And we are actually going to dig into what are called, and this is what we need to do to wrap up this day on intermolecular forces. Guys, we are going to dig into what are called phase diagrams. So here's what I'm going to ask you to do. In your notes, guys, draw yourself a phase diagram. This is a phase diagram. I would suggest that you make this maybe like 5 or 6 inches, even square. Make this dude big. Get all the pieces and the parts and label this thing. And then, guys, we'll tear this apart. And we will talk about phase diagrams. And then, as you know, the only way to really truly understand something is to invite Kathy into the conversation. So, of course, Kathy has something to contribute to this. And then, guys, when we're done with phase diagrams, we will then get into solubility and solution formation. And I've already printed the notes for you for that. For those of you that came in late, you should notice you've got a sheet of paper there that has all the slides today for what you need to know about solubility. So guys, you're going to label the pieces and the parts right now. And then, well, you're going to draw the pieces and parts. And then we're going to talk about this thing and label this thing. And then we're going to chat with Kathy. And then we're going to sort of look at the things that you need to be able to intuit from these things. And then we're going to shift gears and get into solution formation, which is a pretty hard, not hard like difficult, but hard like abrupt change. But really this should be the next day, but we're sort of playing catch up from last time. You guys need another minute? You okay? You guys all good? Eleanor, are you okay? Everybody okay? All right. So, guys, in front of you, you see what is called a phase diagram. And this is not something you learned about in general chemistry. These are brand new to us. I know that you've seen them because you outlined the chapter. But, guys, what I want to do up front is I want to just make you aware of what you need to be able to do with phase diagrams relative to this class, especially on the AP test. So guys, what you're going to see when you see phase diagrams on the AP test, they are actually going to have you use these diagrams to make predictions and to explain observations. Let me say that again. You're going to need to be able to use these diagrams to make predictions and to explain observations. And so, guys, in order to do that, I'm going to suggest that to use them in that capacity, we first of all have got to understand what these things mean and what they're all about. So that's what we're going to do first, is we're just going to label the pieces and the parts. Then once you understand what the pieces and parts are, we're going to be better able to use these in an observational and predictive manner. So, guys, first of all, this. X-axis on a phase diagram is temperature. So guys, if that's true, what is this temperature right there? Not just zero, absolute zero. So guys, the origin of that axis is absolute zero on the temperature scale, if you would like to draw that in. Maybe you remember, but guys, these are all things that you need to know. So guys, on the x-axis, the origin of the graph is absolute zero. But now let's turn our attention to the y-axis. The y-axis is pressure, and guys, that point down there is also zero. So guys, what is zero pressure? it's a vacuum. And so, guys, the y-axis at the origin of the graph is a perfect vacuum other than the substance that is we're studying, because, I mean, obviously it's a phase diagram of a substance, and there's got to be a substance, therefore it's not. So it's zero external pressure. Okay, so we've got absolute zero pressure. So guys, now from there, you should have enough of an understanding of this to think about what these phases are. So guys, when you sit down to the test and you're like, oh crap, I don't remember where the phases are, my suggestion to you would be to do this. In your day-to-day experiences, you probably don't think a lot about pressure changes, but you do think about temperature changes. So, no pun intended, when you freeze up on the test, see what I did right there? When you freeze up on the test, guys, think about temperature. What phase or substance is in at low temperatures? Solid, liquid, or gas? Solid. So why don't you label this solid? I'm realizing, guys, that writing utensil is way too thick. Just a second. Let me see if I can thin that out. Okay, so guys, way over there, that is where we have the solids. Then guys, intermediate temperatures, what phase are we in? Liquids. And then, of course, at our higher temperatures, we're gases. So solids on the left, liquids in the middle, gases on the right. Okay, so then guys, at that point, we can start labeling these arrows. So what do we call it when a solid turns into a liquid? When a solid turns into a liquid? Melting. So this represents melting. What about if we go through the other direction, liquid to solid? Freezing. Then, guys, we can go, which one? Okay, so let's go down to this one, liquid to gases. That, of course, is boiling or vaporization. What about gases to liquids? Condensation, condensing. Then, guys, from there, moving from solids to gases, do you remember? Sublimation. And then, who came in and asked this? What about gases to solids? Deposition or to deposit? Deposition. Okay. Like so. Then, guys, let's talk briefly about these 2 points that are already labeled on your graphs. Kathy is going to do a much better job of this in a moment, but it's worth at least talking about briefly right now. So, guys, this is the point that we call the triple point. Let me define it for you, and you can just write the definition down below. So guys, the triple point is defined as the temperature-pressure combination where all 3 phases of a substance are in equilibrium. Let me say that again. It's the temperature-pressure combination where all 3 phases are in equilibrium. So, guys, let's sort of talk about, and you can draw this if you'd like. What are we going to draw? A beaker. But now, in your beaker, draw yourself an ice cube. Oh, yeah. So guys, literally, this is what's going on. How should we draw that? Which is our equilibrium? Oh, this. Guys, that's what's going on at the triple point. At the triple point, all 3 of these phases are in equilibrium. It's melting and freezing at equilibrium. It is vaporizing and condensing at equilibrium. And it is sublimating and depositing in equilibrium. All three of these things are happening simultaneously. And so guys, if you've got a substance at its triple point, what are you going to see happen? Nothing. Literally nothing. Guys, understand that doesn't mean that nothing's happening, because you've got vapor phase molecules with a little bit more energy crashing into the solid, causing one to sublimate as the other one deposits. You've got a vapor that is condensing to a liquid, all the while the liquid is vaporizing to a gas. Guys, all of these are happening at equilibrium, but the overall change is nothing. You guys okay with that idea? Okay, now Kaylee's going to be very disappointed, but now let's talk about the critical point. So guys, the critical point is the point beyond which it is impossible to condense a gas. If you want to write that down below, you can do that. But guys, the critical point is the point beyond which it is impossible to condense a gas. Fundamentally, it's so stinking hot that it doesn't matter how hard you squeeze it, it won't turn into a liquid. But technically, it's the point beyond which it's impossible to condense a gas. This then creates what is called a super, new word, critical fluid. And guys, I know that this sounds like science fiction, but it's not. These things actually have industrial uses. They actually use supercritical carbon dioxide to decaffeinate coffee. It turns out that caffeine is crazy soluble in supercritical carbon dioxide. And so to decaffeinate coffee beans, they actually soak them in supercritical carbon dioxide. Then they suck off the supercritical fluid. It is kind of like a liquid. They suck off that fluid, and then they allow the carbon dioxide to evaporate, and all the caffeine just collects as a crystal in the bottom of the vat. But they actually use it to decaffeinate coffee beans. So it is actually a practical, real thing. But fundamentally, the idea is this. This is the way I think about it. So you understand that if you take a gas and if you squeeze it, it turns into a liquid. You guys understand that, right? So that's what's going on inside of here. This is air, but it's a liquid because it's under so much pressure inside of here that it compresses it. And so the idea is that what we've done to make this is we've actually taken a gas and we've compressed it to the point that it turns into a liquid. Well, guys, the problem here is that in theory, not in theory, in practice, we can heat this up to such a high temperature that it doesn't matter how hard we squeeze it, it will never liquefy. And that's what's called the critical point. So fundamentally, guys, notice that this line doesn't go on forever. This is not true of the line that represents freezing and melting. You can never heat something hot enough that you can't squeeze it enough to get it to solidify. But with gases and liquids, that's not the case. You guys all good there? Okay, so any questions about these parts of a phase diagram? You're good? Kaylee, are you disappointed? I may not know the answer because I get the sense that you know more about this than I do. So feel free, but you're going to have to let me say I don't know. Oh, yeah, maybe I can help there. Where would you see what? Crystalline liquids? I don't even know what those are. Yeah, so... Oh, I don't know. I mean, is it something? I mean, I really... yeah? Huh. So I know there are like LCDs, right? Liquid crystal displays that are, but my understanding was, but maybe I'm wrong, my understanding that those were just liquids that were flirting with this phase boundary, and we could cause them to do interesting things simply by applying current to them, and that we could move them in and out of their crystalline forms by applying current to it. So my understanding was always that, and I never put that together, but those liquid crystals are actually just things that are right along that boundary. We could certainly look into it more. It's not a part of what we need to know. Go ahead, Isaac. Mm-hmm. Right. Yeah, right. What is? I don't know what you're saying. Let's stop for a second. We don't need to know that. But let me just, was I right in what I said about liquid crystals? Okay, so it really is something that's flirting on that boundary of liquid and solid, and we can use a current to cause the molecules to polarize and then create a solid. Have you guys ever seen this, where there are like windows that you flip a switch and they go black? Have you ever seen that? Like in really like expensive homes, instead of having shades, sometimes they actually have liquid crystal windows, and when there's no current applied to them, they're translucent. You can see through them, and you flip a switch and apply a voltage to them, and they go black. Have you ever seen these? It's really cool. Anyway, all right. So guys, other things about this, please. Yeah, and this is where I think, did you find a video about this? So what does it look, what would you, I didn't get to watch your video. So what your question is what is a supercritical fluid like? In my mind, I always think it just looks like a shiny liquid. What did you find? Yeah. As if they were floating in a liquid. Yeah. Right. But the video that you saw, it didn't look like there was a liquid present. That's it, because it's interesting. The images that I've seen are more liquid-like. Like it looks like a shiny, really flowy liquid. Okay. And it may have been a different substance. In the same way that all liquids don't look the same normally, it could have just been the particular. What did you see them liquefy? Okay. Right. Absolutely. So Maddie, to your point, they're pretty cool. Look them up. But again, guys, you understand, you don't need to understand. You just need to know they exist. You guys all good? You ready for Kathy? Okay. So guys, this then is where Kathy gets involved. And guys, the trick with getting Kathy involved is Kathy is going to bring the application to this. So again, I mentioned to you this idea that you need to be able to look at a phase diagram, and you've got to be able to think about questions like, what if you take a substance at this temperature and squeeze it? Or what if you take a substance at this pressure and cool it? And so guys, you obviously, right, we've got our solids and our liquids and our gases and our temperatures and our pressures and our triple point and our critical point and all these things that we understand. But because this is a video, Kathy can now actually animate some of these things and think about changes. Now guys, along the way, I would like to point something out briefly. How is Kathy's phase diagram different than the one that you drew? Do you see the difference? Yeah, guys, everybody watch Chase's hand. Do it again. Right. Guys, it's the slope of the boundary between the solids and the liquids. Do you see that? What is that slope? Positive or negative? Negative. That makes it water. Guys, the one that you drew is positive. And guys, on Earth, the only substance, well, there's one other that's really exotic thing, but guys, the only substance on Earth that has a negative slope for the phase boundary between solid and liquid is water. But guys, I think you know this. What happens to water when it freezes? Does it expand or contract? It expands, and it's the only substance on Earth that does. You guys understand this, right? If you've got a cup of ice water, where's the ice? Is it floating or on the bottom? It floats. And guys, maybe I thought you understood this. Guys, water is the only substance on Earth where the solid floats in the liquid. Do you guys not know that? So guys, water is the only substance on Earth where the solid is less dense than the liquid. This is why. So guys, when water freezes, because of the size of the water molecules and because of the amazing polarity of these little dudes, when they freeze, when water freezes into this structure, this is ice, you get these huge voids inside of the ice crystal. And guys, there's nothing in here. There's not, like, these are voids. These are empty space. And so guys, water is the only substance on Earth that expands when it freezes. That's why our water pipes break in the winter, right? If there was anything in our water pipes except for water, guys, in the winter our pipes would be fine because when the liquid freezes, it contracts, right? Think about it. Inside a liquid, you've got crazy, and when these things lock in place and freeze, they come together. The only substance that's not the case for is water. Water expands when it freezes, and it's the only substance on Earth that does, right? Do you guys not know that? That's really interesting. So guys, if you think, I mean, it's crazy, right? So if our oceans were made of anything but water, where would the icebergs be? On the bottom. Weird, right? Because again, if our oceans were made of any substance but H2O, the icebergs would be on the bottom because every other substance becomes more dense when it freezes. Liquid water is the only thing that expands when it freezes. Yeah? Oh yeah, like all of the, yeah. Right. I love that you know that. Yeah, so if as the ice crystals form, they would sink to the bottom and the lakes would freeze from the bottom up and they wouldn't have that insulative barrier and all the fish and everything else in the, yeah, would die. And mountain lakes and everything else. There's lots of really interesting implications. So guys, the bottom line as it relates to this is notice that this has a negative slope. That makes it water. We'll talk more about why as we get into this. But guys, understand if you see a phase diagram where that boundary, as Chase pointed out, where this boundary has a negative slope, the only substance on Earth that does that is water. Everything else has a positive slope. We'll talk more in a minute. You guys okay? All right. Come on, Kathy.
A phase diagram indicates the temperature and pressure conditions under which a substance is a solid, a liquid, or a gas. The lines...
Okay, we're going to start over.
A phase diagram...
Is that not Kathy? Kathy must have been sick this day.
...indicates the temperature and...
But I would like to point out that whoever this is, Kathy trusted her. Ooh, could be. All right, I give you Catherine.
A phase diagram indicates the temperature and pressure conditions under which a substance is a solid, a liquid, or a gas. The lines that separate the phases are called phase boundaries. At any point along a phase boundary, the phases exist in equilibrium with one another. For example, in the phase diagram of water, at 1 atmosphere of pressure and 100 degrees Celsius...
You guys think about that. 1 atmosphere of pressure, standard pressure, and then 100 degrees Celsius, the boiling point of water at sea level, 1 atmosphere of pressure.
Liquid water and water vapor exist in equilibrium. This point is known as the normal boiling point of water. Likewise, the temperature at which solid and liquid water are in equilibrium at 1 atmosphere of pressure is known as the normal melting point. The point at which all 3 phase boundaries come together is known as the triple point.
Now guys, look at where the triple point is for water. What temperature is this at? 0.0098 degrees Celsius. So what is that in Fahrenheit? Barely above 32, right? So that's not a very exotic temperature. But guys, look at the pressure. 0.45 or 4.58 torr. Guys, 1 atmosphere of pressure is 760 torr. And this is 4 torr. So guys, this is really stinking close to a vacuum. So amazingly low pressure, not that exciting temperature. That's the triple point of water.
This corresponds to the temperature and pressure combination at which all 3 phases of a substance exist simultaneously in equilibrium. When a sample of solid water or ice at 1 atmosphere of pressure is heated,
Okay, so let's talk. So guys, now look at where we're at. We're at standard pressure, but guys, look at where we are in terms of temperature. We're below 0. Does that help you understand why this is a solid? This is frozen water, right? This is ice. This is below 0. So guys, what's going to happen if we don't change the pressure and if we increase the temperature? Which direction is that dot going to move? Up, down, left, or right? To the right. And as the temperature increases, eventually we'll get to the phase boundary, and then what's the ice going to do? It's going to melt. Here we go.
It will melt when the normal melting point, 0 degrees Celsius, is reached. At this point, water crosses the solid-liquid phase boundary.
Do you see how this can then be used predictively? And guys, the way to use this predictively is to ask yourself, what is changing? In this case, temperature was going up. That means the dot moves to the right, and you would have predicted that eventually it would have melted. Do you get the idea? Okay, now try this.
If the sample is heated further, the liquid water's temperature will increase until it reaches the normal boiling point, 100 degrees Celsius. It will then vaporize, crossing the liquid-gas phase boundary.
Did that make sense as well? Okay, now try this.
Once the liquid is all vaporized, the temperature of the water vapor will increase as more heat is added. If a sample of solid water is heated...
Okay, now try this. So guys, now we're solid water, we're ice, but what's changed? Lower pressure. So guys, we are now below the pressure of the triple point. So what's going to happen if we heat this? Will it melt? It will not. What will it do? Sublimate.
At a pressure below the triple point, it will sublime rather than melt as the temperature increases, because the only phase boundary it will cross is that between the solid and vapor phases.
Did that make sense? Predictions, right? Okay, check this one out.
We can also track the changes in a sample of water as we vary pressure. If the pressure is increased...
So guys, check this out. Now we've got a gas at a relatively, a low pressure, but we're in a gas, so we're at a higher temperature. What's going to happen if we take this gas and squeeze it? Does that dot go up, down, left, or right if we're squeezing it? It will go up, and what will happen to the gas? It will liquefy.
On a sample of water vapor at 110 degrees Celsius, it will condense as it crosses the gas-liquid phase boundary.
And guys, can you even picture that in your brain as you're squeezing those water molecules closer and closer together, and eventually they stick and they form a liquid? Can you see that in your mind's eye? Okay, now try this one. Okay, now guys, we are ice. barely below the triple point. And guys, what is going to happen to this ice if we squeeze it? Which direction will the dot go? If we squeeze it, it will go up. And what will happen to the ice? It will liquefy. Now guys, think about why. So guys, if we take ice and if we squeeze it, look at what happens to the water molecules. It brings these water molecules closer together than they want to be. And as they get closer together than they want to be, their dipoles actually start to push on each other. And as their dipoles push on each other, guys, what is that going to do to the structure of the substance? It collapses and it liquefies. And guys, understand, this is the only substance on earth that does this. I mean, imagine if we take salt and if we squeeze this, what does that do? Well, it just brings the ions even closer together and it increases the attraction. So guys, water is the only substance on earth that when you squeeze it, it melts rather than becoming more solid. Yeah? That's why that line goes backwards. That's why it has a negative slope. So guys, let me play this for you.
Note that a sample of solid water or ice at a temperature slightly below the normal melting point will cross the solid-liquid phase boundary and melt as pressure is increased. This is one of water's unusual properties.
Water's unusual properties. You guys good on that idea? Now check this out.
The critical temperature is the temperature above which a gas cannot be liquefied regardless of the amount of pressure applied. The critical pressure is the pressure necessary to liquefy a gas at the critical temperature.
Holy smokes. Guys, 375 Celsius. That's toasty. But look at the pressure. Guys, 217 times atmospheric pressure. That's terrifying.
The critical point is defined by the critical temperature and the critical pressure. Note that there is no phase boundary beyond the critical point. A substance in this region is known as a supercritical fluid and has properties associated with both gases and liquids.
Okay, so guys, there you have it. A reinforcement of solids and liquids and gases and boiling, vaporization, sublimation, all that other stuff. This unique idea about that line pitching backwards, and then the idea about how to use these things predictively by figuring out whether we are adding or removing heat, adding or removing pressure. Get the idea? Questions about any of that? Okay, so now guys, we've got to have one more conversation and we're done with this. Guys, in order to use this chart predictively, what data do we actually need to know? We need to know the numbers, especially of the critical point or the triple point. Because guys, all of this hinges on the triple point. You'll notice that when we did this, if we were at pressures above the critical point, or the triple point, we'd go solid, liquid, gas. If we're down here, we go sublimation. So guys, it's critical that we know the triple point. So guys, in order to then think about this, let me then take us over to this. And I'd like to share with you one more set of examples, and then we will move past this. So guys, here you go. So on the left, we have water. On the right, we have not water. Guys, how do we know the one on the right is not water? The slope of the boundary between the solids and the liquids. Guys, the one on the right, and we've done the one on the left to death, so I wasn't planning on spending any more time there. But guys, the one on the right is carbon dioxide. But guys, I think you know this. We can actually go and buy carbon dioxide in its solid form at the grocery store. What do you call it? Dry ice. Guys, why is dry? These are the kind of predictions you've got to be able to talk about. Why is dry ice dry? Well, it's because it never exists in the liquid form. Guys, water or carbon dioxide does not exist in the liquid form here on Earth. Why not? Explain it to the person sitting next to you. So guys, let's pull it together and let's talk. In order to have this conversation, what I'd like to do is I'd like to start with water. So guys, this is where we live here on Earth in terms of temperatures and pressures. We hover amazingly close to 1 atmosphere of pressure, and our temperatures are like 20 is room temperature, 40 is like Africa hot. So we live sort of in that region. So guys, bringing this region together, that sort of places us in here. But guys, if this is the region where we live in here, water can be a solid, a liquid, and a gas because that's sort of where our life happens. But guys, look at this. Over here for carbon dioxide, that's literally our world. But guys, look at where the triple point is. 5 atmospheres more pressure. And guys, we don't see those kinds of pressures here on Earth. As a result, because we don't have these kinds of pressures, our world is below the triple point. And below the triple point, it is impossible to be a liquid. Because that's an interesting point. Below the triple point, a substance cannot be a liquid. As a result, all this can be is a solid and a gas, and that's why carbon dioxide sublimates. But you ready for an interesting thought? We actually will see liquid carbon dioxide on Earth. Where? The bottom of the ocean. Guys, there's actually enough pressure down there that you can actually liquefy carbon dioxide. It's not atmospheric pressure, it's the pressure of the ocean. And down there, we actually do see liquid carbon dioxide, but understand it's at freakishly high pressures. You've got to be 5 times atmospheric pressure for this to work. Okay, so guys, you okay on these ideas? Anything about phase diagrams that you want to explore? You guys all okay? Okay, so there's one more thing we need to talk about, and I'm going to leave this up to you as I do every year. Well, let's do this. Guys, don't try to write any of this down. It's going to go quick. But guys, there are a couple things that you need to know about solids. It's in your book. You may just want to write down review 12.1 and 12.2. But guys, look over 12.1 and 12.2, but we're going to do this just quickly right now. So guys, solids. There are 2 different types of solids. There are what are called crystalline solids, and there are what are called amorphous solids. So guys, I think you're going to find this pretty straightforward. Ready? This is a crystalline solid. Why? Because it exists as crystals of table salt. This is a crystalline solid. Why? Because it exists as crystals of ice. Got the idea? What about sugar? Crystalline? Also crystalline. But guys, what about this? Pencil erasers. Crystalline? No, it's a completely different type of solid. It is an amorphous solid. So guys, what does the prefix A mean? Without, and morph means shape. So there's another type of solid called an amorphous solid, and guys, they do not have orderly crystalline structures. If you could look inside an eraser, it would just be a jumble of molecules with no ordered repeated pattern to them. You'll notice that things like rubber and glass and things like that are what are called amorphous. So guys, you can just think of amorphous solids as not being crystalline. You okay with those two classes, if you will? Yeah. Yeah, so are we. Yeah, and it's actually really interesting, right? I actually put glass up there because of that. You're like, wait a minute, I've broken a glass and I've seen the crystals. We still don't know if well, it's weird. Not only do we not know if glass is crystalline or amorphous, we don't even know if it's a solid. There's really, really fascinating research going on all the time that would propose that glass is actually a very viscous liquid. Yeah, we've seen examples of it that like early glass, like we have glass that's hundreds of years old and it puddles. It does, yeah. But what flows? Well, liquids, right? So solid glass, if you let it sit over decades and centuries, will puddle, making us think that it actually could be a liquid. So the jury is still out. Look it up. Look up, not now, but look up, is glass a solid? And understand this isn't some weird conspiracy theory thing. This is actually science. We don't know. The jury is still out on whether glass is a liquid, a really thick liquid, or a solid. But we know for sure that it is amorphous. And here's why. Do you know what glass is made of? It's silicon dioxide. So silicon dioxide in its crystalline form is sand. So that's what silicon dioxide looks like as a crystal, is sand. But we know that glass is not like sand. So if you don't know, the way that they make glass is they actually take sand and they melt it. And then they freeze it really fast. And when it freezes so quickly that it can't form that regular crystalline structure. So it's amorphous. That's actually what makes it transparent. Because there's no ordered rhyme or reason to it, light can get through it. Actually look it up. They just did a really interesting, I think it was Veritasium video on, no, it was actually, It's Okay to Be Smart. Because do you know that channel, It's Okay to Be Smart? Anyway, look it up. They actually did a really fascinating video on why is glass clear. And the reason is because it's amorphous. Because if it was a regular crystalline structure, it would be sand, and light can't get through that. So anyway, you guys good on this? Okay, then this, guys, and I think, well, let's just do this. We've got a minute. Guys, you need to scratch these down. We're now talking about crystalline solids. And guys, you need to know that there are 4 different kinds of crystalline solids. They go like this. There are molecular solids. There are covalent network solids. There are ionic solids, and there are metallic solids. That humming is driving me crazy. Okay. So, guys, the easiest way to think about these things is by looking at examples. So let's do molecular solids first. And guys, understand all of these are crystalline. So this is a subset of crystalline. And there are 4 types. Molecular solids are sugars. But guys, what forces hold sugar together as a crystalline solid? Intermolecular forces. Guys, these are tied together by IMFs. If you could picture a crystal of sugar, you've got these sugar molecules as the points in a crystal lattice, but the forces that hold the crystal lattice together are intermolecular forces. That's why sugar melts at a relatively low temperature. You're not breaking the covalent bonds inside the sugar, you're just breaking the IMFs. Is that one okay? Okay, then guys, covalent network solids, think diamond. So guys, this is what it looks like inside of diamond, the hardest substance on Earth. What are the gray sticks? Covalent bonds. That's where the name covalent network solid comes from. Guys, it's kind of like an ionic substance, but the difference is that all the forces of attraction are covalent bonds. Those are even stronger than ionic bonds. So when you think covalent network solid, it is a crystal, but all of the forces that hold it together are crazy strong covalent bonds, which makes diamond the strongest substance on Earth. So guys, if you ever run into a substance on a test, nudge, nudge, wink, wink, next week, if you ever run into a substance on a test that is like ridiculously strong or ridiculously stable or has a ridiculously high melting point, it's going to be a covalent network solid, because those are the things that are so tightly tied together. Then down here, we've done this to death. This is ionic bonds and salt lattices. And then guys, finally, metallic solids. You learned about this last year. Think sea of electrons. So guys, there you have it. Here's what I'm going to suggest. We need to do solution stuff. We've already done it last year, so it will be review with a little finer point. So guys, this is what well, here, let me pause recording, and then I want to talk with you about how the rest of the day is going to proceed. No, you can just, no, you don't. So, oh shoot, you can't see this. Wait, why can't you see this? What happened? Oh, wait, here we go. So guys, relative to what we just did with phase diagrams and the such, guys, this is your homework from that. Do I need to wait for you to write it down, or can you just lift it? You want me to wait? Or shoot a picture of it? Or just look at it in the notes? Okay, you guys good there? All right, so guys, from there then, the conversation changes, and we now start talking about solution formation. So guys, you have the notes in front of you. You're going to find out that I skipped a couple of the slides simply because they were either so elementary that you didn't need them, or they were largely review. But guys, what we need to do now is we need to wrap our arms fully around this idea of how solutions form. So guys, one of the video or one of the slides that I stole from you is, not surprisingly, the Kathy video with salt dissolving in water. But guys, in order to really understand what's going on with that video, guys, we need to bring some of the things that we know about thermodynamics into the conversation. So that's what's going to make today a little bit different. You already know that the water grabs a hold of the ions, pulls it off like little dump trucks. All that stuff is true. But guys, fundamentally, you've got to understand the energetics of this. Why do some things dissolve? Why do other things not dissolve? You need to understand more, building upon what you already know. So guys, with that said, you'll notice that I pulled some of the stuff out of your notes like this. Good? Solutions contain two parts, solute and solvent. The solute's being dissolved, the solvent is doing the dissolving. Good there? You'll notice that that slide is not, did everybody get the slides? Did you all get this piece of paper? Did anyone not? You guys are good? So guys, that's not there because I assumed you know that. Is that okay? You're all right? I'm not getting much back. You're good? Okay. So then guys, in addition to that, as we do this, for our purposes in this class, for the most part, we're going to say that our solvents are liquids, typically water, although you know in lab today, our solvent is going to be cyclohexane. But for the most part, our solvent will be a liquid, and then our solutes traditionally are solids, but we're also going to talk about dissolving liquids in liquids and gases in liquids, and we'll get to that at the end of the day. So you guys, okay. So guys, with that said, important terms, these you have in front of you. I would encourage you to take notes into the notes, maybe circle things if you need. But guys, these are the terms that you need to know when we talk about solutions. First of all, the term is solvation. And guys, we're going to go back over these terms in a second when we watch the video. But for now, guys, understand that solvation, can you even picture the video where we pause it and the water molecules are all surrounding the ions? Guys, that's called solvation. It's the clustering of the solvent particles around the solute. Now guys, when your solvent is water, we have a more specific term. It's not solvation, we call it hydration. So hydration is solvation when the solvent's water. Again, you have the notes so you can keep up as you go. Then guys, this is important, saturated solutions. Saturated solutions are solutions that you can't get any more solute to dissolve into. So guys, they are solutions where you can keep adding solid, but no more will dissolve. They're saturated. You can't get any more solute to dissolve into the solution. Does that make sense? Go ahead. Yes. Dang, Chase, that's interesting. I was thinking about your specific example, but right, you weren't seeing temperature changes anymore, right? And probably what happened is you saturated your solution, so you weren't getting more stuff to dissolve into the water. Yeah, that's a great connection. So guys, let me do this with you really quickly. You don't need to know this, but if you understand this, I think you're going to find it kind of compelling. So guys, a saturated solution, you can't get anything else to dissolve in, right? That is actually not technically the definition of a saturated solution. Please do not write this down, but I'm going to give you the actual definition. And guys, if you understand what we're talking about, you're going to find this interesting. You ready? So this is the actual definition of a saturated solution. Listen carefully. A solution in contact with its solute. That's it. A solution in contact with its solute. And guys, if you understand what a saturated solution is, you should find that definition interesting. Do you see how that works? Let's draw a picture. And you don't need to draw this, but the idea is this. Because imagine again that we have a beaker, and in the beaker we've got some water, and we're dropping salt into the water. So that's a crystal of salt. So we're adding salt, it dissolves, it dissolves, it dissolves. But now guys, we get to the point where we have the solution and it's in contact with its solute. How do we know for sure that that solution is saturated? What if it weren't saturated? What would this do? Dissolve. Do you now understand the beauty of that definition? So guys, the only way that a solution can be in contact with its solute is if the solution is saturated, because otherwise the solute would dissolve. Do you understand the idea? You'll go ahead. Yeah. Yeah. That's a really interesting question. So if it's saturated in one solute, is it therefore saturated in all? And interestingly, the answer is not necessarily. So if you had a solution that was saturated in table salt, you could maybe get a different salt to dissolve. Not as much, but you still could get some to dissolve. So, but understand, not as much. So there is a relationship. It does cut down on capacity, but it doesn't disregard any dissolving of another solute at all. That's interesting. So guys, you get on saturated solutions? Okay, so then finishing up our list of terms you need to know. Guys, solubility then is actually a technical term. It is defined as the amount of solute that you can dissolve in a given amount of solution at a given temperature. Guys, typically it's grams of solute in 100 grams of water. We'll talk more about that later. But typically the units are grams of solute in 100 milliliters of solution, or if it's water, it's 100 grams of water, because those are the same. And then, guys, another term that you need to know is miscible. When liquids dissolve in liquids, we don't talk about their solubility. We talk about their miscibility. But, guys, the trick is this. You can't saturate, thank you, Diana, you can't saturate liquid-liquid solutions. Think about that. If you dump alcohol in water, the alcohol dissolves, but you can't add so much alcohol to water that eventually you get a layer of alcohol and a layer of water alcohol mixed together. So guys, when liquids dissolve into liquids, it happens differently and you can't saturate them. Technically what happens is if you add so much alcohol to water, eventually alcohol becomes the solvent and not the solute, and it just keeps going. So when you get liquid-liquid solutions forming, you can't saturate them. We call this miscibility. And then, guys, if something doesn't dissolve, if a liquid doesn't dissolve in a liquid, technically it's not insoluble, it's immiscible. So don't get too caught up in that, but understand that especially when you get to college, you'll have professors that will talk about miscibility rather than solubility when you're talking about liquids and liquids, and just understand that they're kind of related. The only difference is you can't saturate a liquid-liquid solution. Okay, so guys, nice to have the notes, right? Are you all caught up? Anything else there you want to talk about? All right, then you know what it's time to do. Kathy. And it actually is Kathy this time. So guys, let me get ready for Kathy.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact.
It wasn't your turn. Kathy gets a little excited sometimes. Okay, so guys, here we go. So looking at this video with fresh eyes, thinking about the terms and the concepts that you understand, guys, we're going to watch it twice.
When an ionic substance, such as sodium chloride, is
That's Kathy, not Catherine.
placed in water, water molecules.
What are you guys seeing right there? What are you seeing? Solvation, but it's water, so what do we call it? Hydration. Oh, look at those molecules coming in.
Interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anion.
Hydration like crazy, right?
With the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
You guys good? So using these terms that we now know, we've got solvation, we've got hydration. Solubility would be the amount of salt that we can dissolve in the water. See how that all comes together? Okay. So now, guys, this. We are now going to take this conversation and we're going to move it forward and talk about the stuff that's new, the thermodynamics of this entire process. Now, guys, with this said, a little disclaimer. When we talk about this, we are not going to include entropy. We understand that disorder does play a factor in this, but guys, you only need to understand what we're about to talk about on the level of enthalpy and not as it applies to entropy. So guys, with that said, obviously this is not stuff you need to draw into your notes. But guys, now with everything that you know about intermolecular forces, we can now have a really intelligent conversation about this question. Why does salt dissolve in water? Why does salt dissolve in water? So guys, in order to answer that question, let's talk about the forces that we see at play on the screen. So, and you know what? Let me do this carefully so that this lines up with our notes. Okay, so guys, what is that force right there? What kind of force is it? What is it, intra or intermolecular? It is intramolecular, and what is it? It's an ionic bond. So guys, one of the forces that we need to keep track of is an ionic bond, and let me make sure I'm doing this right. We are going to call that force number 1. Okay. Now guys, what are other forces that we see at play? Well, here is another force of attraction. Guys, and it's a combination of things, but what is the strongest force that we see represented there? Hydrogen forces. We are going to call this force number 2, and this is what we call, I'm just going to call it an H force, just for simplicity. Oh, you guys okay on that? But now, guys, there's another force at play, and we need to talk about this, and that would be this force right here. I drew it in a couple locations. It's not actually an angle. Let me do that again, because that's a little sloppy. So, guys, we've got this force. Let's just draw it there. What's that force right there? An ion dipole force. So, guys, this is an ion dipole force, and we're going to call that force number 3. So guys, we can now answer the question, why does salt dissolve in water? Why does salt dissolve in water? Because 3 is bigger than 1 plus 2. 3 is bigger than 1 plus 2. Guys, the reason that salt dissolves in water is because 3 is bigger than 1 plus 2. But now, guys, we've got to lend signs to this. So, guys, what is happening to the ionic bonds? Are they during dissolving? Are they forming or breaking? They are breaking. Is that endo or exothermic? Breaking is endothermic, and so we're in the system, right? We are in the salt and the water, so if we're breaking bonds, that is endothermic. So is that positive or negative in terms of sign? So guys, one of the things that you're going to find challenging, I think you are even right now, about this class is that you cannot compartmentalize information. I understand that sometimes the details get a little fuzzy, but there are general and important concepts that you do not have the luxury of just tucking away because we're done with that unit. One of those fundamental ideas is that breaking things always absorbs energy. And because we are in the system, and if energy is going in, what is the sign? Positive. So guys, here's the deal. Some of you have been coming to me over the last couple days and weeks and saying, hey, Mr. Namper, I'm concerned. I'm worried about the test. I'm worried about where I am in the class. And guys, if you're really trying to think about things that you can do to avoid, to address the worry, one of those is make sure, guys, that you're not losing sight of the important big details from the past. Because this is hypercritical. Breaking things involves an input of energy, and that always means the sign is positive because energy is going into the system. So now you're going, wait a minute, how do I do that better? How do I hang on to these things? And guys, here's one of the things I would suggest. Whether you know it or not, there's always a mental conversation that's going on inside of your brain. And guys, here's the problem. You've been trained for the last 11 or 12 years that information comes in packets. And once you're done with that packet, that unit, when the test is over, you can just conveniently forget everything you just learned. But guys, there needs to come this active level of engagement that says, no. I cannot let my brain do that. I need to keep these important ideas circulating and cycling through my brain, not telling myself it's okay to forget, but reminding myself that this class is cumulative and there are big ideas that I can't just allow to shrug off my shoulders like water off my back as the days go on. And guys, one of those is energy goes in when things break. So guys, breaking ionic bonds is positive. Then guys, what about breaking the hydrogen forces in the water? Also positive. Energy is going in here because those are breaking. But what about the ion dipole forces? Are they forming or breaking? They are forming. As a result, when bonds form, what happens to energy? Energy is released. So what is the sign? That would be negative. So guys, this then is the answer to why does salt dissolve in water? And the answer is because these ion dipole forces are so stinking strong that the energy that's released when they form is greater than the energy that has to go in to dissociate the ionic bonds and the hydrogen forces. Now again, guys, some of you are thinking, wait a minute, when I did this, I had a salt that was endothermic when it dissolved. Again, entropy is a factor. But guys, the big idea is this. Which salts dissolve? What explains why things dissolve in water? And the reason that things dissolve in water is because the attraction between the water and the thing is so strong that it allows the thing and the water to move away from itself and latch together with the solute and the solvent. Does that make sense? Is that okay? Okay, so guys, this then leads to a hazardous proposal. Turn to the next slide where it says enthalpy changes and it says 3 processes. You see that? Guys, here's the risk. What you see in front of you then is a retelling of those 3 ideas. When a solution forms, the solute has to split apart. That's endothermic. That's breaking the ionic bonds in our salt. Then guys, the solvent particles have got to separate. That's endothermic. That was breaking the hydrogen forces. But then, guys, we've got to form these solute-solvent interactions, and that's exothermic. But, guys, please be careful. These numbers are not ordinal. Do you know what ordinal means? In order. It's not step 1. It's not step 2. It is not step 3. All of these things are happening at the same time. We simply give them numbers 1, 2, and 3 so that this makes more sense. So guys, let's talk. Let's talk about what we're looking at here. I'm going to go, I'll just stay with red as my color. But guys, let's take a look. You've got this in front of you. So guys, this then is the way that we think of the enthalpy changes in solution forming processes. But guys, again, these are not step by step. It looks step by step because there's no other way to represent this. But here's the idea. We start with a solute and a solvent. And the idea is that we'll say the first step is that the solute particles, the ionic forces break. Then guys, the next step is that the solute particles, or the solvent particles, in this case the hydrogen bonds, separate. And so now what we've got is separate solvent and separate solute particles. And then guys, a bunch of energy is released when, in this case with our video, the ion dipole forces form, and that's the overall energy picture. Now guys, with some of these solutes, and this is always true, energy always goes in to break the solute, energy always goes in to break the solvent, energy always comes out when the solute and the solvent interact. Now guys, understand that some of this happens endothermically and some of it can happen exothermically. This is a net exothermic process because the energy of the solution is lower than the solute and the solvent. Guys, these are the things that always will dissolve. If you've got an exothermic solution process, those things almost always dissolve. But guys, these dissolve less likely. These are net endothermic processes. And going back to what we know from thermochemistry, if something is endothermic, it doesn't tend to be spontaneous. Now, can this still dissolve? Yeah, but what has to be true? What offsets the energy change? the entropy change. We need an offsetting entropy change for this to dissolve. But guys, the fundamental idea is if the net change is exothermic, that tends to be spontaneous. If the net change is endothermic, less likely to be spontaneous, but some do dissolve because of the entropy change. But that's that. So guys, you good on these ideas? Is that okay? All right. So where does that then take us next? So guys, what we need to do then is, and really the next slide is a summary. Did I even give it to you? It looks like this. Did I give you this? Okay. And so guys, the bottom line is all this is saying is that if we have a substance and the overall energy change is exothermic, those tend to be soluble. So if the heated solution is exothermic, those tend to dissolve. If they're highly endothermic, they won't unless there's a really huge increase in disorder. Is that all okay? Okay. So guys, this then takes us to an interesting next thought. So guys, what we need to do now is we now need, and we got this and one more idea, and then we're going to wrap up. Guys, you should have this. Did I give you the whole table? Oh, good. So guys, don't get caught up in the information in this table other than that you can understand the driving principle. But guys, I'm going to give you the full picture. Then I'm going to give you the driving principle. Then we're going to talk about how to talk about this on the test. Okay? So the chart is actually the chemistry. Then we're going to talk about the driving, well, the idea, the way to memorize this. And then we'll talk about how to talk about it on the test. So guys, the big question that we're going to answer now is why do some things dissolve in water? Why do other things not? But also then, guys, importantly, why do some things dissolve in other stuff when they don't dissolve in water? So guys, for example, does salt dissolve in water? Yeah, absolutely. But does salt dissolve in gasoline? It doesn't. Guys, salt does not dissolve in gasoline. What about this? Does oil dissolve in water? No, but it does dissolve in gasoline. And guys, the question is why? Why does salt dissolve in water but not gas? And why does oil dissolve in gas but not water? And so guys, what you're going to find is that there's a really simple way to memorize this. But what I want to do is I want to talk you through the logic of this. So guys, notice what I've got here for you. Over here are your solvents. We've got a polar solvent like water. We've got a non-polar solvent like gasoline. Then over here, we've got a polar solvent, or polar solute like salt, and then we've got a non-polar solvent like oil. So guys, let's be really clear before we get into this more deeply. Does salt dissolve in water? Yes. Does oil dissolve in water? No. Okay, what about this? Does salt dissolve in gasoline? No. But does oil dissolve in gasoline? Yeah, so the question is why? And guys, the answer goes like this. So guys, here's what we know. So looking at this example first, inside our solute, the salt, we've got really strong forces, ionic bonds. Guys, inside our solvent, we've got, this was the video. Inside our solvent, we've got really strong forces, hydrogen forces. But then, guys, when these get together, we have very, very strong ion dipole forces, and that causes this to be soluble. Do you get the idea? Okay, now this. Let's go over here. Guys, now we have oil, and the forces of attraction inside the oil are weak. Here's a question. What are the forces that hold oil together? What kind of intermolecular force? They are actually induced dipoles. Guys, oil molecules are very, very symmetrical. The forces that hold them together are induced dipole forces. Now, guys, understand that they're strong enough to hold it together as a liquid, but you get the idea. But now, guys, what about inside the solvent? Well, our solvent is still water, and those are hydrogen forces, and they're strong. But, guys, imagine this. Shoot, I'm not even in a position to build it. Let me show this to you. So guys, imagine what happens when we get these together. I'm going to build you an oil molecule really. Well, this is not going to be big enough to be oil. But guys, imagine that this just goes on and on and on and on and on, because that's all oils are, just long strings of carbon with stuff stuck to it. But guys, imagine this. Imagine if we have this really long, symmetrical, nonpolar molecule, and imagine if we dump it in water. Where does the water attract this nonpolar molecule? Where's it going to stick? It doesn't. And that's the point. Guys, this molecule, like an oil molecule, is long and it's symmetrical and it doesn't have points of polarity. The only reason it sticks together at all is it's sloshy and it sticks to other sloshy things. But guys, there's nowhere for the water molecule to attach to this. There's no such thing as a dipole, induced dipole force, right? There's nowhere for this to stick. And because there's nowhere for this to stick, the water molecules don't stick to the oil molecules. And as a result, the forces of attraction are very weak and this doesn't dissolve. You get the idea? Okay, now let's go down here. Guys, gasoline, also a really, really big nonpolar molecule. What are the forces of attraction inside gasoline? Also induced dipoles. So guys, inside the solvent, we've got salt. Those are ionic bonds. But inside the liquid, inside the solvent, the gasoline, those are induced dipoles, not very strong. So now guys, the game has changed. Now this is our solvent. Let's say this is gas now instead of oil. So guys, where's the gas going to stick to the ions? Well, nowhere, right? Because induced dipoles can't stick to ions, so there's nowhere for these to attract, and as a result, the salt doesn't dissolve in the gas. Get the idea? So guys, these have very weak forces, and it's insoluble. So now guys, what about this? What about when we put gasoline and oil together? So guys, what are the forces of attraction inside the oil? Well, they're induced dipoles. What are the forces of attraction inside the gasoline? Also induced dipoles. But guess what, guys? These not only can induce dipoles in themselves, they can induce dipoles in each other. And unfortunately, I don't have another one of these to represent. So if one was gas and one was oil, they actually start inducing dipoles in each other. And when they do, they kind of create these strongish induced dipole attractions between the two of them, and that's why it dissolves. So guys, we've got we've got a nonpolar solvent and a nonpolar solute, and they induce dipoles in each other, and that creates intermolecular forces that are strong enough that it causes it to dissolve. Do you get the idea? Okay, so now guys, how are you going to summarize this table? So guys, which pairings create solutions? What's the overall summary of the table? Strong to strong or weak to weak. Yeah? Strong to strong or weak to weak. Guys, the way we summarize that is this. This you want to write down. Oh, it's already in your notes, right? Guys, like dissolves like. If you ever write this on a test, you're going to get 0 credit. Guys, you do not get to say like dissolves like. But guys, what like dissolves like means is solutions form strong to strong and weak to weak. Does that make sense? So how do you talk about it on the test? And that's the important part. How do you talk about this on the test? So guys, let's use our examples as examples. How would you talk about the idea that salt dissolves in water? And we would say something like this. The very polar water molecules are strongly attracted to the salt ions, allowing the salt to dissolve in water. Do you see how that goes? The very polar. Now, is this hydrogen forces? Are there hydrogen forces between the water and the salt? No. Hydrogen forces only form with hydrogens bonded to oxygen, nitrogen, and fluorine. But guys, we would say that the very polar water molecules are strongly attracted to the salt ions, allowing it to dissolve. Now guys, what about this? Let's talk about the other one that does dissolve. How would we explain oil dissolving in gasoline? And we would say something like this. the nonpolar gasoline molecules induce dipoles in the nonpolar oil molecules, and these induced dipoles cause the oil to dissolve into the gas. Is that okay? Yeah. They do, but so this and that's exact. And I want to be really careful about this, Maddie, because I actually taught it the way that you're thinking about it in the future, and it screwed people up. But let's talk about that when we look at the ones that don't dissolve. Okay, but you're absolutely right. Don't these all contain induced dipoles? And the answer is yes, but let's talk about this and then talk about how we're not going to talk about it. Okay, so guys, are you good on the ones that do dissolve? Okay, now let's do this. Why does oil not dissolve in water? And we might say something like this. We might say that the non-polar oil molecules are not attractive to the polar water molecules. Is that okay? Now let's talk about your point. But wait a minute. Isn't water, like any substance, capable of exhibiting induced dipoles? And so couldn't a water molecule, in theory, induce a dipole in an oil molecule? And the answer is yes, and that actually does happen. So why doesn't it cause the stuff to dissolve? And the reason is because it's not strong enough to overcome the hydrogen forces in the water in the first place. Right? Do you understand why we're not talking about it now? So the idea is this. Exactly. Precisely. Yeah, and so that's part of it too. That water is so small that it's not very polarizable, but it is polarizable. And so the water, in theory, can induce a dipole in the oil molecules, but that that induced dipole force between the two of them is so much weaker than the hydrogen forces that already exist in the water that it's not enough to get the water to leave other water molecules and grab a hold of oil. Again, that's why we don't talk. So let's do this. When are the induced dipole forces between a solute and a solvent strong enough to get them to dissolve? And it's only in the case when the forces that hold the solute and solvent to themselves are also induced dipoles. Any other example, the forces aren't strong enough to get the other to play together. Okay, and then guys, finally here, how would we talk about the idea that this is not soluble? And the idea, again, is that the forces of attraction, so the nonpolar gasoline molecules, these guys, the nonpolar gasoline molecules don't have any points of polarity that are attracted to the ions, and as a result, it can't overcome the ionic forces and rip this apart. Does that make sense? Go ahead. Kind of, but I'm scared to go there. So we're about to talk about solubility. And solubility's definition is the amount of stuff that will dissolve in 100 milliliters of water. And some of that is a function of polarity. But that's not it. It's also a function of size. It's a function of mass. It's also a function of entropy. So that, while you're right in what you said, it's not complete. Go ahead. I don't know if I know what a hydrated oil is. It sounds like something from a makeup commercial. Oh, like a okay, so you're talking about not a hydrated oil, but a hydrated salt. Thanks, buddy. So I don't know what a hydrated oil is, but hydrated salts still wouldn't be able to dissolve nonpolar things because you've still got water, which isn't attracted to nonpolar, and salt, which isn't attracted to nonpolar. So that wouldn't go. Okay, you guys good on these ideas? So not only, guys, if you can just remember like dissolves like, and then remember how to talk about this. And guys, when you talk about this, it's all about talking about the force between the solute and the solvent.
So that means that a non-polar gas like CH4
Yes.
and oil?
Will dissolve? I have no idea. That's interesting. So can you get natural gas to dissolve in cooking oil? That sounds like a really, really cool science fair project. And then what would happen if you threw a match in it? Santiago, I've never thought about that. So, I mean, so did you hear his question? Could you get methane, CH4, totally non-polar, well, not totally, but non-polar, symmetrical, could you get that to dissolve in oil? If the answer was no, I would guess it's because CH4 is so small that it's not polarizable enough to create forces of attraction strong enough to get it to stick to the oil. But I'd love for the answer to be yes, just because that would be cool. How could we test this? We could get a beaker of cooking oil, stick a hose from here into it, but how would we know if it dissolved? The mass would change, right? That would be cool. I want to know. I have no idea. I love the question, though. You guys got the idea? You okay? Question more things here besides all the interesting what ifs? Okay, so guys, we've got one more thing to do, and we're going to wrap this up. Just general broad brush stroke ideas. You need to understand how different factors influence solubility. And guys, you've got this in front of you. I'm going to click through it, but then we're going to look at some examples. So guys, the first factor that you need to know that affects solubility is pressure. And again, when we're having these conversations, let's let our solvent be water, okay? So guys, the solubilities of liquids and solids in liquids are not significantly affected by pressure. So this is the idea. If you've got a cup of water and if you dump alcohol in it and then you squish it, you can't get more alcohol to dissolve. You already know that. It's a miscibility issue. But guys, the solubility of liquids in liquids doesn't depend upon pressure. But neither does solids. So guys, if you add salt to water and then you squeeze it, like if you were... I mean, really, this is what we're talking about. Let me see if I can find one quickly. So guys, if you were to take a syringe and if you were to put some salt water in here, saturated salt solution, and then if you were to squeeze it, you couldn't get more salt to dissolve in the water because the solubility of liquids and solids doesn't depend on pressure. Is that okay? What about gases? Does the solubility of gases depend upon pressure? And guys, obviously, because we set it aside, the answer is yes, right? But guys, do you mind if I borrow this? You guys, you know this from experience because all it's water, right? But if this was like a Coke, and if you shake a Coke and then let the lid off, what's going to happen? It goes everywhere. Why? Guys, why does that happen? Well, let's think about it. You guys understand, and again, this isn't a soda, but we're pretending. But guys, if you have a soda, this is carbonated water. How do they make carbonated water? They dissolve carbon dioxide in water. Literally, that's how they make it. And so, guys, then they screw a lid on this. And when you screw a lid on this, that creates pressure, right? Vapor pressure. The carbon dioxide is trying to escape. And as the carbon dioxide escapes, it gets up in that little bit of headspace. But then it pushes back down on the solution. And you end up with pressure pushing down on the water. And that keeps the carbon dioxide dissolved in the water. But then, guys, when you screw the lid off, what happens to the pressure? The pressure goes down and the solubility goes down and all the carbon dioxide can no longer stay dissolved in the water and some of the carbon dioxide comes out of solution and it all ends up shooting out the top. So guys, that's the relationship between pressure and solubility. The higher the pressure, the greater the solubility. The lower the pressure, the lower the solubility. And that's what this is all about. The solubility of a gas in a liquid is increased as the pressure goes up. But guys, maybe you can even picture that, right? Here, let me get some water in here. So the idea is this. So guys, here we've got water in a syringe. But what's up here? Air and water vapor, right? Because the water's evaporating. So we've got water vapor up here and we've got air up here. And let's just say the air is nitrogen. It's 70% nitrogen. But guys, if I do this and I squeeze, what happened to the amount of nitrogen up here? Did it go up or down? It doesn't stay the same. What happens? It goes down. Where does some of the nitrogen go? It dissolves into the water. But guys, can you almost picture it? It's like we're driving the nitrogen into the water by squeezing it. And that's literally what you're doing. When you squeeze this, you're literally forcing some of the nitrogen to dissolve into the water. And then when we pull down on this, we're decreasing the pressure. And some of the nitrogen is like, woohoo, look at all the space up here. Let's jump up there and let's get back into the gas phase. Guys, understand that if I were to pull down on that with my finger gone, then that wouldn't change the solubility because we're not changing the pressure. So the only reason this changes is if I put my finger up there, because now pulling down, we've decreased the pressure up here, and that allows some of the nitrogen to come out of solution and go up into the vapor phase. You get the idea? So increasing pressure increases solubility of gases. Does that sit okay? You guys okay on that? Okay. Then guys, the other one that we need to know is, oh, that's not working. Guys, the other one that we need to know, oh, and by the way, that has a name. It's called Henry's Law. You may see that on the test. But guys, Henry's Law just simply says that if you increase the pressure, you increase the solubility. And then guys, the last one is temperature. And this one's interesting. Guys, in liquid solvents, the solubility of solids goes up with temperature. So if you add a, well, let's say this, more salt will dissolve in boiling water than will dissolve in cold water. Does that make sense? So guys, the solubility of solids goes up with temperature. I keep forgetting my board's off. But guys, conversely, the solubility of gases goes down with temperature. So it looks like this. So guys, on both of these axes, you have, and you guys have these, right? Yeah. So on both of these axes, you have temperature moving from low to high, left to right. But on the left, you've got the solubility of solids. Notice that this is in grams per 100 grams of water. Those are our units of solubility. And as the temperature goes up, you'll notice that all of these, except for cerium sulfate, and I don't know why, all of them have positive slopes, meaning that as the temperature goes up, the solubility goes up. But then guys, looking here, you'll notice that these are all gases, and as the temperature goes up, the solubility goes down. Is that okay? So guys, let's talk a little bit about some interesting things with this. Guys, first of all, why? Why would the solubility of gases go down as the temperature goes up? What happens to the molecules as they get hotter? They move faster, right? And they evaporate more readily. So the idea is that these molecules want to jump into the gas phase, and because they're gases to begin with, it just means they go back up into the gas phase and then they're not dissolved in the water anymore. You get the idea? You understand, though, guys, the implications of this, right? That's why you don't fish on a hot summer day. Have you ever noticed that? Guys, if you're a fisherman, you always fish early in the morning and late in the evening. Why do you not fish in the middle of the day? Well, in the middle of the day, it's hot. And when it gets hot, guys, there's less oxygen dissolved in the water. And if there's less oxygen dissolved in the water, the fish don't have as much oxygen to breathe, and their response to that is to get deep and to lay low because they're literally suffocating. And so they wait until the morning and the evening when it's cooler, more air, more oxygen dissolves into the water, and they can be more active and go out and look for food, because in the middle of the day, there's less oxygen dissolved in the water and it's harder for them to breathe. Because guys, you do understand, right, that fish do not breathe the oxygen that's tied up in H2O. They breathe the oxygen that dissolves in the water, not the oxygen. You knew that, right? Even if you didn't know that, say yes. Okay. All right. And then, guys, looking at this other graph over here, there's one little thing that we need to talk about, and then we're going to wrap this up. So, guys, notice what happens to all these solubilities. As the temperature goes up, the solubility goes up. More solid can dissolve in the liquid. You guys good on that idea? Okay. So now, guys, there's one more thing that we need to talk about just really quickly. I did not give you the slides for this, but we're going to talk about it anyway. Let me make sure I've got my writing utensil. And guys, the conversation goes like this. There is a term that you're going to want to write down, and then I'll show you a quick video, and then we'll call it quits. So guys, do this. Keep your eye on potassium nitrate. You ready? So guys, here's what we're going to do. We're going to take a beaker of water. Let's not do that. Let's do potassium chloride. It's more linear. Let's do potassium chloride. So guys, keep your eye on potassium chloride. So let's say we take a beaker of water and we heat it up to, let's say, 90 degrees. We can't get to 100 because we're not at sea level. So guys, say we take a beaker of water and we heat it up to 90 Celsius, which is right below the boiling point. Guys, how much potassium chloride can we dissolve in 100 grams of 90 degree water? How much can we get to dissolve in there? 50. Let's call it 55. It's probably a little below that, but let's call it 55 grams. So guys, the solubility of potassium chloride is 55 grams at 90 degrees Celsius. So guys, imagine that we do that. Imagine that we have 100 grams of water, we add 55 grams of potassium chloride, we stir it, and it all dissolves. Then guys, we let that beaker sit, and we let it cool down. And it cools down to room temperature, and let's call room temperature 20 degrees Celsius. Guys, at 20 degrees Celsius, how much potassium chloride can dissolve in the water? 30. So it's this line right, where'd it go? This one here, so maybe 32 grams. So guys, here's the question. 23 less grams of potassium chloride can dissolve at room temperature than can dissolve when it's hot. So guys, if we were to do this, 55 grams at 90 degrees, let it cool down to 20, what would we see happen in the beaker? What would we see happen in the beaker? Maddie is suggesting salt crystals. How much salt crystals? Maybe 23 grams of salt crystals. But guys, here's the thing that's interesting. If we do this really carefully with very clean glassware, we won't see anything change. Let me say that again. If we do this very carefully with very clean glassware, we will not see anything change. And what that means is at 20 degrees Celsius, we will still have 55 grams of stuff dissolved in the water. So first of all, what allows it to stay in solution? And guys, the answer is this. There's nothing for the crystals to form upon. In order for crystals to form, there has to be a surface upon which those crystals can form. And guys, if our glassware is really, really clean, there are no surfaces. It can't happen on the glass because the glass isn't polar. And guys, there are no surfaces upon which these crystals can form. And as a result, the additional 23 grams, that's the difference, right? The additional 23 grams of potassium chloride stays dissolved in the water. Guys, there's a name for this. It is what is called a supersaturated solution. Scratch it down. It's called, underneath the graphs, just write down supersaturated. Guys, this is what is called a supersaturated solution. So fundamentally, guys, a supersaturated solution is a solution that's got more stuff dissolved in it than it should, simply because you saturate a solution at a high temperature and then let it cool. And as it cools, if it doesn't have anywhere to form crystals, the stuff just stays dissolved. But then, guys, this gets really interesting. Because guess what we can do? Well, we can introduce a surface upon which these crystals can form. And guys, when we do that, really interesting things happen. Let me unhide these slides. That's not it. There we go. So guys, this is actually what this looks like. So this, oops, oh sorry, I went to the wrong slide. Oh shoot, it didn't unhide. Just a moment. Unskip and unskip. Okay. So guys, this is actually what this looks like. This is a close-up view of supersaturated sodium acetate. And what you're, well here, let me just play it. So see what they did? They dropped in right here inside those tweezers is actually a crystal of sodium acetate. So they heated sodium acetate up to close to boiling, dissolved a pant load of sodium acetate in there, and then let it cool off. And this is supersaturated. Guys, there's a lot of sodium acetate in there that should not be dissolved in the water. And when they throw a seed crystal in here, guys, this crystal just grows and grows and grows because all of that sodium acetate that shouldn't be dissolved in water all of a sudden has a surface that it can crystallize on, and it goes absolutely crazy. It's kind of fun stuff. Whoa, what's this? What was that? I've never watched the video that far. I don't know what that was. All right. So then, guys, the only thing that could possibly make this more entertaining is to get a bunch of stupid high school chemistry kids around the beaker and then record their response as we do this. See the crystal go in? I don't know if you can see that or not. It goes in right... Again, this is sodium. Do you see it? So guys, the seed crystal is right there.
Oh my god. No, it looks like a little puffball.
Which is actually not stupid. It's kind of neat that they think it's interesting.
Wait, you gotta turn it upside down as soon as it's frozen.
Frozen. It's not freezing. What is it doing? Precipitating.
Oh my god, it's solid.
So far we have kids kicking the floor, and we have puffball, and we have freezing. None of which is right. Well, actually, and that's the thing that's really interesting about this, Autumn, is, and it's kind of fun. Whoa. Okay, I'm as bad as these high school kids. But guys, here's the thing that's interesting.
Wait, you gotta turn it upside down as soon as it's...
Hear what the kid said? Turn it upside down. And actually, I'm embarrassed to say I clipped off the video. He actually does that.
Frozen.
Frozen, no.
Oh my god, it's solid.
Now guys, the thing that's crazy is this. Later on in the video, and again, I cropped it, he actually does pick up the beaker and flip it upside down, and it all stays in the beaker. So literally what's happened is it has turned to a solid in that we've got this crystal structure now with all of this salt that didn't want to stay dissolved in solution. But then, guys, what happens is the water gets trapped inside of that crystal. And so literally it's kind of like a hydrated salt, only in reverse. So now instead of water being entrapped inside the crystal, kind of like the crystal's trapped. Anyway, it's supersaturated solutions. Yeah. Exactly. It would all go back into solution. So it was really frustrating. So you know that the AP test is the first week of May, right? Well, you didn't know that. So guys, the AP test is the first week of May. And the rub is, what are we going to do in this class after the AP test? And guys, there's lots of answers to that question, and we'll talk more about this after Christmas. But guys, one of the things that one of my classes chose to do is they wanted to do other experiments. And one of the things that they wanted to do was make supersaturated solutions. And so we did, except for we could never get them to work. We tried to make a supersaturated solution out of sodium acetate, and the problem was we couldn't get our glassware clean enough. So we would heat up water, distilled water, dissolve the sodium acetate in there, but what would happen is we could never quite get all of the sodium acetate to completely dissolve, and as it cooled, there were always little invisible crystals of sodium acetate that they would crystallize on. So then we got creative and we tried to filter it. So we would heat up the water with the sodium acetate, then filter it into another clean beaker, thinking that we could never get the crystals out completely. So we could never get it to supersaturate. It was really frustrating. But anyway, you get the idea with supersaturation? Okay, so guys, let's do this. Here then is your homework from this one. And we're done.